and be back to alma mater. So thanks to organizers for doing this beautiful job of organization of such a big conference. And I respect, of course, it's already the evening in Europe. The America's people are fresh and full of energy. We are all a bit tired, right? So, and when we are tired, we are thinking about being a little lazy. So I am doing computer algebra, inspired, of course, from pure algebra and all that since more than 20 years. And I have implemented tens of thousands of lines of code, released systems. All of this is open source and advanced things. And actually, but I'm also getting tired from time to time. And I want just in this of the artificial intelligence, which is coming back. Yes, so in the 70s, what we're doing right now in computer algebra was symbolic artificial intelligence. But the artificial intelligence of today is not like this. It went a much more linear way of thinking and doing things. Well, they achieved progresses because of statistics and interplay of many things. But at that time, symbolic artificial intelligence was abandoned because of its high algorithmic complexity, and not only. Because as soon as we are living, pardon, quasi community finitely generated world, then we face much more difficulties, which seem strange to a person who grew up with a commutative background. We have terminological algorithm. It is a procedure which terminates. Otherwise, it's just called procedure. So we suddenly encounter very basic functions, which will not terminate. And we have no chance to terminate. Then we appear objects, and we cannot provide a canonical form to these objects. Or if it exists, it's combinatorically hard to compute. And we have, of course, in terms of complexity theory, we have the decidability issues. Nevertheless, in this talk, I will talk about some applications of these tools. We are doing free associative algebras with units, and we will need two-sided Grobner or Grobner-Kirchhoff basis, division algorithm, and the Grobner lifting, which I will explain in a little more details. So here are the recent papers on topics and another. Under number 3, you see the URL to the website where you can download, which is a part of a big Germany-based project from ComSingular, which has a significant Ukrainian part in it by our school from the Department of Algebra at Kyiv University. And this is called the subsystem responsible for free algebras. It's called letter place because it used so-called letter place technology for a coding object. So the paper below is a joint work with Leonard Schmidt. And another paper is under construction, and we are talking about identities of matrices. So what are the matrix identities? For the seconds, imagine that we are dealing with square matrices as such, or with block matrices, which consist in matrices. They are matrices with entries in some field for a moment. And well, the first identity, it is non-trivial because it takes us 2 lines to prove. So it's not yet trivial. Then another one is happening where we try to adjoin elements, and this is called the Hua identity, which is the statement of Hua lemma, and Hua lemma is part of the statement of Hua's theorem about division rings. So it is a translation in a sense of the product in such of sums and inverses of parts. So you see, in addition to the usual ring situation, we also will do some inverses of the matrices, and by doing this, we automatically adjoin about the domain of definition. So if I am writing C minus Y minus A inverse, it means that C minus Y minus A is invertible. So let's take the world as it is. Then one has the third identity. Is quite interesting. It's how the sum of inverses and inverse translate in the nice product. And this is another interesting thing which is used. Why these things are important. In particular, they are of huge importance in numerical mathematics, because they are doing with matrices all the time, and contributions of some matrices to products or to inverses or to that is of big importance. And let's have a look at this one, And this is the illustration to my statement that there is no canonical form. All of these things are equal, and it is more or less, so it's even equal to the inverse of A plus UCV. Perhaps those of you who have seen something like this is a celebrated Sherman, Morrison, Woodbury matrix identity, which has thousands of implementations and thousands of ways of doing it. At the moment, it is for square matrices. Later on, I will show you, we have also proved the theorem for rectangular matrices. And below, you see, this is the famous Schur complement formulas, which tells us how we should do the things where we invert the matrices in blocks, right? And again, this matrix identity can be proved for non-square blocks, but I will say just a minute. So there's a big world of these things, and all these identities are pleasant for our algebraic eyes. Yes, every algebraic say, well, these are objects we can touch, this is an object we can manipulate with. So can we prove these identities in automatic manner, just sitting down with the software which is there and just press the button and wait for the answer and then print it on the paper and submit to some journal? Well, not because the proofs of such identities by hands are usually very peculiarly technical. And still, there are many publications which are devoted to the proofs. So now let's see the general line of attack. So K is a field, A is an associative K algebra. And for instance, I will illustrate the story, the methodology with Hua's identity. This is how it is written. So let's say we're M times A matrices over a field. First, we choose the symbols. And here I will say some words what we do exactly. Then the symbols X will become our variables, and we consider the Freemannoid and elements of it are monomials in these variables, and then the free associative algebra is a K monoid algebra of this Freemannoid is of course composed of polynomials. Then we extract a little from this algebra A of matrices, and we will go to the free associative algebra, the mother of all associative algebras. And we do this, we call this evaluation. You will see in a second what does it mean. So at the moment, just if I'm writing A minus 1, it doesn't mean the inverse. It's just a placeholder. It's just a name saying that these objects in the free algebra will then, after elevation, become the real inverses. But in order for doing this, we will need a relation. So what we do, we just in a sense considering sort of representation of our identity in terms of finally presented algebra. So this is the evaluation. Small a will be set to big A, and this inverses to this, and small am is the m times m identity matrix. So we even can address different sizes of identities and matrices of different sizes, which a little later on. So as I said, at the moment for small a's, they are not equal to 1 and not equal to each other, but after the evaluation was where we have big letters, yes, in the algebra it will become the. So this is the idea, and recall that the symbol small a is not invertible because it's just a placeholder, it's just a name. And the names are ubiquitous. Then we write down the set of relations between our variables, which we extract from these things. And usually it will be seen as something like we adjoin to our free algebra first a new polynomial variable, and it will be a two-sided inverse to some quantity, right? Whether it is just a or a polynomial or things like this. And then we need to solve a word problem. If we have now this polynomial, we can write it down in the algebra which we have constructed. So, and word problems are also called ideal membership problems. And in free associative algebras in particular, this is the instance of Grobner basis theory, which needed to be taken because our things are in general not graded, not homogeneous, but still finitely generated. So how does this work? We need to fix a monomial total ordering. on the set of positively compatible with multiplication. So if something was smaller than something, multiplying it by a monomial on both sides, even on left or on the right, keeps our relation there. And then we take, so Lm is a leading monomial, and then we do this division with remainder, which is a classical algorithm. And by the way, this guy will necessarily stop because the argument here is the totality of the ordering. So the fact that the totality of well ordering, it should be well ordering, then it always terminates. And one can say informally that a set G is a Grobner basis of the ideal, two-sided ideal, generates if and only if any polynomial in this ideal reduces to zero modulo G with this operation. And this is actually the property of a Grobner basis. Even in a commutative case, multivariate division with remainder will be unique if and only if your set is a Grobner basis. Well, another peculiarity here in the two-sided situations in the free algebra is that our element has this double sum presentation via the generators. Say the generators are small gi, then we have one big sum over here ranging over these gi's, and then we can have left-hand factors and right-hand factors, both of them, and so on and so on. So this is presentation of an element in ideal, and this is two-sided. This causes some technical troubles. And this is also called the two-sided presentation of an element F in the ideal generated by G. And also this expression is a certificate of ideal membership, because elements of such a form are necessarily sitting inside of ideals. And this is the proof of our identity in our setup. Precisely this presentation of the identity we want to see. But it's better to see it as to talk a long while. So consider the whole identity. We have chosen the symbols. Yes, so these are the stages of our big way. So, and we'll come to the identity. So W will be the polynomial represented. So here, what we do, we subsequently add new variables and add relations which come from metric inverses. Well, and this will be x6 and x7. These are too small to deserve our names, and let's collect the relations. So these are just that A is inverse of A minus 1, yes, and M times N. Fine. This is for C minus 1, and this is now for x6, these two relations, for x7, this relation. So, and now we compute by some black magic, we compute the Grobner basis. Well, wait a second, not yet. These are the trivia. These are the relations we have to add for explaining that IM is the M times M identity matrix. Sorry, I was just way too fast. So we have to add this stuff. And it seems that we are completing our presentation of this all inverse. And then we compute the Grobner basis, and then we do division with remainder with respect to Grobner basis. And here it is a certificate. So all these polynomials in the initial set are numbered. And it is possible to show that this element has this presentation. This presentation is not unique. As soon as we find one, we find a certificate, because we can check it either by other piece of software or even by hands if we have enough time and enough zeal to do this. So this is how the things work. This seems to be, and now we translate formally it's back to the big letters, and in big letters we have this proof. So to the right, this funny expression to the right is actually a proof that this guy is this follows from these relations. Well, but up to now nobody has objected. The word problem over free associative algebra is widely known to be undecided. Well, the free associative algebra is not Syrian, and even with the Grobner basis theory, they are usually infinite, and we have no control on them. Well, how do we tackle all the things? So in computer algebra, usually we start with a theory, and we look towards procedures and algorithms, and then we prove correctness of them, and then we prove termination. And then we try or do the implementation and then compute the things. In such a model, when we are dealing with this, not necessarily things, but there is a notion of length. Well, you may think about just the usual degree of a polynomials. So it is a new part of our setup. We specify the degree bound. Some more computations, we increase the degree bound is start over, because we, so in general, even in order to recover new elements of some low degrees, we have to get somehow high. This is the problem in the non-graded situation. But by increasing the bounds, we get more and more information on the ideal. And so something is possible, and surprisingly many things are possible in this setup. So now a nice result, not yet published, but it will come soon, which means that if you give me a valid identity, then to produce a proof of it in the form of the certificate is algorithmic. It will necessarily terminate. Whereas to check whether the identity is valid remains in generally undecided. And well, in the proof we use such an interesting objects which were derived in the second 70s by Amit Sur, then Maurice Kohn and Konrad now in the end of 90s have proved that the word problem over the free field is decidable. And our computation embeds into the free field. So why semi-decidability? Because this is called when we have a positive outcome, then the algorithm terminates. Otherwise, we don't know. So we don't have a check of validity, but we have machinery to generate the proofs of valid identities. So this is nice, and this shows that actually what we are doing will necessarily terminate for valid identities, and we can produce more. So now, how do we proceed from square matrices setup to more general rectangular? Okay, we augment each matrix now gets its format description, additionally rows and column size. And then, of course, we can say that the products are valid if a monomial considered of these things augmented with rows and columns are staying in the right form. So this is just a justification that we can determine valid products by valid monomials in such a way. And our colleagues, and in a sense competitors from the Austrian Linz, Regensburger, Raab, and so on, they have pursued the way of pass algebras. Right, because now we have passes and so on, but with Schmitz we have found actually a faster way, and this is precisely the content of this lemma. If the input, what we feed to a Grosvenor basis or a normal form or division with remainder algorithm, consists of expressions which are only composed in the correct format, then not only the output, the Grosvenor basis, not only the division with remainder, not only the remainder, but any intermediate expression in a Grosvenor basis algorithm will be kept in the Pascal format. So it means with this proposition, we don't have to change a single line of code in our implementation, but by this way we get the proofs also of identities for rectangular matrices, which is quite a nice thing. So let's do a little more, and this is the deduction. Grosvenor bases, despite their heaviness and the nature, so they reveal the truth about your idea, right? They reveal the truth about your relations, and they can be used for deductions, which is very, very important. And I stress this fact that this is really a point where it is worth trying. So we take now a modification of Sherman, Morrison, Woodbury identity, now without knowledge that we have the inverse. So you might remember this inverse of A plus UCV, inverse of this matrix has this 7 or 8 different expressions on the slide number 2. So our setup, A is m times m, it's invertible. Let's have C, you will see for the moment Y, and then these also matrices are invertible. Then we can prove that it is invertible, that this guy is invertible. Well, we invoke to Moore-Penrose inverse because it's algebraic. And it always exists now, so P will be the Moore-Penrose inverse of the matrix S plus U CV. Now, again, at first, we just have used small letters to encode these guys above. And here we have written down the relations between just reflecting the two-sided inverses. Now we have added the red relations. This is the axioms of the Moore-Penrose inverse. Well, we have augmented now. You see, we have different identity matrices, IL, IM, and so on. And we have also the star. The star is a formal involution, which is like complex conjugation and or transpose. We just have an element, say A times B minus C. We apply involution to it and write it in the real form B star A star minus C star. So this is just what we do. And then we get the green guy. And now some magenta guys were those one who are under skirt. Now reinterpreted with this whole story gives us this relation, which tells us together that the field is C, that nothing else but this happens. So we have found an inverse. So we have not only proved that this matrix is invertible, but we have computed an inverse automatically without knowing anything that we have found. And you can reproduce these computations. You see, it still fits on one page. Of course, you cannot do it by hands anymore, or provided you have infinite time. But this is already proof which we can present, and this proof has been majorly assisted by our software. So I will just show you the overview. With Schmitz, we have been doing many different directions, many different proofs, and also this is interesting that we have even the characterization of a rank. So we have this the composition of a matrix into a matrix of full rank, and so on, so on, so on. What is new, for instance, that Sherman, Morrison, Woodbury can be also formulated not for inverses, but for Moore-Penrose inverses. And we did it also because Moore-Penrose inverses are algebraic and of algebraic nature. And well, these proofs you don't want to see necessarily, but they are there and you can check them automatically. So, and let's play a small play. I think I still have some minutes. I want to demonstrate you how the software works. And for this reason, let's, it's like it can be thought as a common effort, right? So like the work in progress, if we have enough time and some people from the audience, we could just finish this as a paper today and submit some. So 2x2 matrices with say, let's say SL2, of course, to GL2 we can do more, and over some commutative ring. What is given? It's an old story coming from the invariance theory. We have the traces, right? So we have just one here because with the one determinant one, so the matrices are invertible, and we have a subgroup generated by the matrices A and B. So these are the characteristic polynomials of both of them. Now the two traces are the parameters, and of course then the products AB and BA are also SL2 things, and let's introduce trace of AB and trace of BA as an additional one. So these are four equations which I feed into my system. You will see how this works, and then I will just run a Grosvenor basis and let's see what will be common out as a proof. So I run the system singular, everyone download it and use, and so this is it. I'm putting some input, and this is the idea I call relations. You see 19 members of it. So I is the 2x2 identity matrix, and for instance here relation 11, it just reflects it squares itself. And the usual information we started with is given here. The rest, because we want to work over a ring, we keep traces as four variables which are not invertible, but they are commutative with this other, but can do also non-commutative part. So now I compute the Grosvenor base. So you have seen these are the relations we fit in, and the Grobner basis is much smaller, has just certain elements, and it has only elements of degree up to 2. And yet let's see what is the first element of this basis. Well, it tells us that the trace of AB is equal to trace of BA. My system doesn't know linear algebra. It's never encoded. It was just what was written above, that we have matrices, characteristic polynomials of degree 2 with these parameters trace A and trace B. And much more interesting, with 12, we recover also quite a fun fact that all these degree 4 guys disappear, and then we have this skew relation between BA and AB. So this is how we can do the deduction. Moreover, the degrees of the elements are all 1 or 2, means that we are already having the finite Grobner basis. So this is the whole truth about this situation. And now, in order to show you what is behind, let me activate the protocol and just show what was happening behind. So I'm computing on regular desktop computer. So it tells us 1 megabyte was used. We have done up to total degree 7 in our variables. You see, we started with 4 and ended with 2, but we went up to 7, and we considered so-called 48 critical pairs. So it means there is some work. And in order to show you that we can also now produce a proof how the system came to this. So let me give, so GB2, this is the element 1. So this tells us if we divide by trace A, then trace of BA is equal to trace B. And this one is a vector out of 19 components. And in each component, we have, instead of this symbol and cgen of 17, we have to insert the 17th generator of our ideal. So you see, the certificate for this small fact, the trace of AB is equal to trace to BA, is not easy at all. And it uses all these relations. Let us see what is about the guy number 12. Yes, we have now 2 expressions. The second one is smaller, and this is number 12. This is this skew relation between the 2 guys. So this skew relation, which establishes actually the formula how we transpose them. So this is how the things are working. You see, we are working with big objects, but nevertheless we are fast, and we are doing well with memory. So this complete application, just to show you that sometimes Grobner basis is an ideal tool for guessing. It's never can say what will be coming out of the computation. And actually, these questions on invariance theory go back to Sibirsky, 68, Alexan, 89. It was observed that because of these traces being equal and this relation, we can now derive closed expressions for trace of an arbitrary matrix from the group generated by A and B. And we can even produce a closed formulas. For instance, the trace of the 5th power of A is this polynomial in trace A of degree 5. And of course, you can do it for trace of BAB and so on, where these expressions come along. So actually, these 2 papers, Sibirsky and Alexan, they were doing it by hands. But nowadays we have a machinery, and of course, we can also come to statements, to the theorems, which will be inspired from this whole machinery, which is now freely available to everyone. And I think this is the end of my story. I'm open to answer any questions, whether there will be some. Thank you very much for your attention.